In this lesson, we are going to talk about modeling exponential growth and decay. What exactly we mean by modeling is that you are going to have an application problem, and then you have to decide what type of equations are best to fit the data. We are going to consider three different types of equations here. We are going to talk about linear, quadratic, and exponential. And based on the modeling, then we can decide on what we call extrapolation and interpolation. Interpolation means that if you have a series of data points, you can use, by this type of modeling, you can find the value of the function and at a point which is within the data set. And extrapolation means that you can use this modeling to find a point outside the data points. We are going to see examples as we go along. The first example is a biology student which is studying the population growth of a bacterial culture. The mass of the culture is measured and it's represented in this table of values. We do not know the initial mass, which is at time 0, but we know the next 7 hours of the mass, which is given in table of values. We are going to define r squared, which is the coefficient of determination, and it's a constant, which is going to tell us how well an equation fits a given set of data. What I mean by this is that given this table of values, I can either fit a linear equation which goes through majority of these points, or I can fit a quadratic or an exponential. Now, if I want to decide which one is best, either I can look at the graph, the scatter plot, or I can look at a number r squared. We are not going to talk about how you find this number. We are going to use technology, especially Desmos, which is going to give us a number r squared, and then we are going to compare these r squared for different type of modeling, linear, quadratic, or exponential. So, if this table of value is given, the first part of the question says, make a scatter plot of the table. So I'm going to go and use Desmos to plot a scatter plot. We are going to click on the plus sign here, and then we choose the table. Now I'm going to enter the given values, except 0 at time 0 because we have no idea what the value is. So the first one is 1, 2, 3, 4, 5, 6, and 7. And the y values are 10, 21, 43, 82, 168, 320, and 475. Now, right now, all the data points are shown. It fits the graph, no problem. But if you find out that the graph is not the way you want it, then you have to go to settings here, and you have to set the x values and the y values. For instance, here the x values are from 1 to 8. Here it's negative 1.465 to 12.076, which which is a good domain, which includes all these values. If it is not, then change these numbers here. For the y, the same thing. For instance, here it has negative 14.93. I can go ahead and change this one to the lowest one, which is 10, but I'm going to pick, let's say, 0, and the highest one is 120, which is lower than 475, because 475 is my maximum. So I'm going to change this one to 500. Now you can see that everything is fit in the view here, and this shows you the graph. By looking at this graph, you may say automatically that a linear one is not really a good fit to this set of data points. An exponential is very good fit, and also a quadratic, because a quadratic goes like this. So the two possibilities are quadratic and exponential function. The next part of the question says perform a linear regression analysis. What this exactly means is that try different types of equations and compare them and see which one is the best one here. We are going to only consider linear, quadratic, and exponential, and we will see which one is going to fit the data the best. Okay, back to Desmos. This is the table of values here, and this is our scatter plot. Now the question is that how am I going to use Desmos to do regression analysis here? Click on the empty or blank row here, and we know that in general the equation of a line is y is equal mx plus b. So start typing y and then number 1. Then it's going to make it y1 subscript 1. Then instead of using equal sign, use this character, tilde. And then type mx, but x again, x1 plus b. Now you can see that this is the equation of line of best fit here. You can see that this equation almost goes through 2 points, and the other points are all off the line. Now look at the values here. R squared, which is the constant of determination here, is 0.8591. So this is the first one. Now let's go and do a quadratic regression. We are going to use the standard form of a quadratic equation, which is ax squared plus bx plus c. So I'm going to do the same thing. y1, then the tilde sign is ax1 squared plus bx1 plus c. Now this is the quadratic of best fit. You can see that it almost goes through all the points except, let's say this point. It fits very, very good, and you can see by the number r squared here is 0.9959. By the way, r squared is a number between 0 and 1. It can't be negative and it can't be greater than 1. The best fit, the best value is 1. This means that the equation fits the data exactly. And 0 means that the equation does not fit at all. That's the worst case scenario. The best case scenario is when r squared is 1. And you can see that this quadratic regression is almost 1. It's very good fit. Now the last one, we are going to check for exponential. Remember, the exponential equation is y is equal to ab exponent x. So I'm going to do the same thing. y1 tilde sign ab exponent x1. Now, if you want to see exactly where the graph is, I'm going to turn off the linear regression and the quadratic. You can see this is the exponential function which best fits the data. Again, it's something like quadratic. It goes almost through all the points, and the constant of the determination r squared is 0.89, which is lower than quadratic here. So you will be tempted to say that the quadratic is the best one, but you have to look at the context of the problem. So let's turn on the quadratic one. The problem with the quadratic is it doesn't fit with the context of the problem. What this graph is telling us is that to the left of this point, which is this side, the mass of the bacteria is decreasing, then it gets to this point and starts increasing, which is incorrect. It doesn't really, matches with the problem. But with the exponential one, it is telling us that it starts with almost zero, and as the time passes on, it increases. So you cannot always look at the r squared and decide which one is the best one. You have to look at the context of the problem. In this case, in this problem, probably the exponential one fits the data the best. The next part of the problem says complete the table for different regressions: linear, quadratic, and exponential, and record your values. So looking at this linear regression, you can see that m is 75.6 rounded to one decimal, b is negative 142.7. For quadratic, a is 17.4, b is negative 63.8, and c is 66.4. And for exponential, a is 11.2 and b is 1.7. We need these values. So the first method, linear, the equation is rounded to one decimal, is y is equal to 75.6x minus 142.7, and we found that the r squared is 0.859. For quadratic, I'm going to show with Q, we found that y is equal to 17.4 x squared minus 63.8 x plus 66.4, and we found that the r squared is 0.9959. And the exponential one, we found that a and b rounded to one decimal gives us the equation 11.2 times 1.7 exponent x, and the r squared was 0.89. The next part of the question is asking to find the value of the mass at hour 8 and hour 9. We have two possibilities. One, we can use these equations, which are shown here, for different values of x. For instance, for x equal to 8, which is time 8, we can replace x here with 8 and then evaluate this one. And the same here and here, or for 9. Or we can use decimals, because we have already plotted the line of best fit or quadratic of best fit and also exponential of best fit. So I'm going to use the second method, and I'm going to show you how you can use decimals to do this one. Okay, back to decimals. This is line of best fit, this is exponential of best fit, and this is quadratic of best fit. How am I going to use these graphs to find the values at 8 and 9? First of all, we said that the time is 8. So to do that one, time 8 is a line which goes up here, because this one represents the time. So I'm going to plot x equal to 8. You can see this perpendicular line is the represented time t equal to 8. To see the linear one, if I click here, you can see that the value of mass when time is 8 is 462. For 9, I'm going to go down here and I'm going to plot x equal to 9. This is the line x equal to 9, and you can see that the value of the mass is 538. The same, let's look at, for instance, this time, let's look at the exponential one. Before I do that, let me turn off the line now. So the line is gone. And also let's turn off the exponential so we can see only the quadratic here. For time t equal to 8, you can see that the value is 671.5, but since we are talking about the mass and we said that we're going to round it to 1, so it's going to be 671.6. For t equal to 9, you can see that the value is 904.1. For exponential 1, I'm going to turn off the quadratic and then I'm going to turn on the exponential. Now for t equal to 8, you can see that the mass is 841, rounded to 1 decimal. And for t is equal to 9 is going to be 1443.3. So this is how we can use the graph to find the value of the mass. So going back here, I can write that mass for linear is 462 grams. For quadratic is 671, and for exponential is 840. At 9 hours, it's 538, 904, and 1443. The last part of the question says, which equation fits the data best? Looking at the R square, again we said that quadratic has a value which is much closer to 1 than any other equation that we have here, but because of the context of the problem, we said the best one is exponential. And the worst one is linear, You can see the reason is that the r squared is farther away from 1 compared to the other two. The next part of the question says, using the best equation, which was the exponential that fits the data, find the initial population. To do this one, either again we can use the equations that we found before, or we can use the graph. I'm going to use the exponential one, and you can see the graph of exponential. This is when the time is 0. So if I click here, you can see that the value is 11.171. So we can say that the initial value based on our regression, which is exponential, is about 11.171 gram. Now I'm going just to refresh your memory that we said the equation for an exponential function is of the form of p is equal to p0 times b exponent t, where p0 is initial value, b is the base, okay, and t is the time here. Now we said that if b is greater than 1, then it's going to be exponential growth, and if b is between 1 and 0, then it's going to be an exponential decay. In a national park, a wolf population increased by a factor of 1.078. This means that our b value is 1.078 every year over a 10-year period, beginning at 1997. The formula that we have is p is equal to 124 times 1.078 exponent n. We are supposed to use technology to graph the relation, so we are going to go ahead and use decimals. So back in decimals, we are going to type the equation y is equal to 124 times open bracket 1.078 exponent x, and this is the graph of the function. Now, the only problem we have here is we know that x here represents number of years since 1997, and x cannot be negative. So how can I make sure that the x values are going to be only positive here? To do this one, hit space and then open curly bracket and then type x has to be greater than or equal to 0. You can see now that the x values are only positive. The negative one is taken out. The next question says, what was the wolf population in 1997? Remember that n in our equation represents the number of years since 1997. So the number of wolves at 1997 is going to be n equal to 0, because the time since 1997 is going to be 0. So let's go back to our decimals again. Now, when n is equal to 0, it represents the y-axis here. So this is the value, which is 124. So this means that the initial population of the wolves at 1997 is 124. So the answer here is 124. The next part of the question says, what was the wolf population in 2007? Again, you can use either the equation or we can use the decimals. So I prefer to use the decimals, which is a practice to see how we can use the graph to evaluate questions like this one. So this is our decimals again. Now I have to find the number of wolves in 2007. Remember that n represents the number of years since 1997. So this means that I have to plot the line. Remember, this represents the number of years since 1997. Okay, so I have to plot x is equal to 2007 minus 1997, whatever this value is. If you look at the graph, this is 10, which is correct because 2007 minus 1997 is 10 years. If you look here, the point of intersection is the number of wolves, and you can see it's about 262 or 263 wolves here. 262 to 263, depending on the rounding, either up or down. The next question says, a sheet of translucent glass 1 millimeter thick reduces the intensity of the light passing through it. Light intensity is further reduced as more sheets of glass are placed together, as shown in the table. So, when there is no glass, 100% of the light passes through the glass. If there is only one glass, only 89.1% goes. If you have two glasses, only 79.4% goes through it, and so forth. The first part of the question says, we define the reduction rate of a sheet of glass is the percent of which the light intensity is reduced. What is the light intensity reduction rate of a single sheet of glass? Because of the definition here, it says the reduction rate is the percent of which the light intensity is reduced. So what I have to do is that we have to find the difference between 89.1 and 100. So we say that the reduction rate, let's call it RR, reduction rate, is 100% minus 89.1%. If we do this subtraction, we find that this one is 10.9%. So the reduction rate for this example is 10.9%. The next part of the question says, how many sheets of glass are needed to reduce the light intensity by 1/2? If you look at the table here, 1/2 means 50%, which relates to this column of the table. So this means that there are 6 glasses which we need to reduce the light intensity by 50%. The next part of the question says, use a graphing calculator to graph this relation. So again, it means that we have to go to decimals and start drawing the scatter plot. So back to decimals. Again, as usual, we click on plus sign, then table, and start typing the numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8. At 0, we have 100%, then we have 89.1, then we have 79.4, then we have 70.7, So this is how the graph looks like, the scatter plot. And you can see that this just resembles an exponential decay. The next part of the question says, use your graph to determine how many sheets of glass are needed to reduce the light intensity to about 25%. The way we do it is that we are going to go back to Desmos, and since the y-axis represents the percentage of the light which is going to pass through, we have to draw the line y equal to 25 and then look at the point of intersection. So this is our graph again. Remember, this one represents the percentage and this one represents the number of classes. To see how many classes are needed to reduce the light by 25%, we are going to plot y is equal to 25. Now, this one, you can see that the graph does not intercept with this line. So what I'm going to do is that I'm going to find the exponential of best fit that goes through these points and then find the point of intersection with that graph. So again, we're going to go here, we're going to write y1 tilde sign AB exponent x1. So this gives us the equation, and you can see that the r squared here is 1. This means that it's the best fit. This equation is the correct equation here. And here is the point of intersection. This means that I need 25 glasses to reduce the amount of light that passes through the glasses to 25%.